Welcome to my channel. We are continuing our sequence on integration by parts, and today we are dealing with the following problem. Before diving in it, let me say a couple of words. It's been a while I was not recording any videos, but with a new breed we are continuing, and for those of you who are new here, it's a channel of a hedgehog. We are making some videos on mathematics, physics, mainly for undergrads. I realized I never introduced this channel to my audience. Nevertheless, we have some time, and for this point it's enough, and perhaps in the future we'll dive more into this matter, but let's keep some intrigue. Alright, moving back to our problem, we have second to the 5 of x dx. How we will approach this problem? First, let's see what we can do here. We have second to the 5. We can write second to the 5 as second cube x, second square x, so that then we can use integration by parts, right? Because we know that the antiderivative of second square x is tangent x, and then we can find the derivative of second to the cube x and obtain what we'll obtain. We'll have something like second square x multiplied by derivative of second x, which is second x tangent x. Then we have the form of second cube x times tangent x, but we also have tangent x here after using integration by parts, so it will be tangent square x, right? I hope it's right. So then we'll again have second x. So it's just a short outline, like because we have a degree of 5, I suppose we'll deal with the integral of second x multiple of times. So I propose using some reduction formulas. Like we can first introduce I n, which will be integral from 0 to pi over 4 of second to the n of x dx, and in the end we'll need to find I of 5, right? But let's first derive some formula for I sub n. Alright, let's just use that idea I proposed earlier, namely we can write this as integral from 0 to pi over 4 of second to the n minus 2 of x times second square x dx, and here we can use integration by parts. We have second to the n minus 2 of x and second square x dx. How we'll use it? We can write that u is equal to second to the n minus 2 of x. Then let's compute du, which will be n minus 2 times second to the n minus 3 of x, and then we must multiply this by derivative of second of x, which is, if you remember, tangent of x multiplied by second of x. So we can write this as multiplied by tangent of x second of x. Okay, we finished with u. Let's see our dv, and we took it as second square of x dx. Then it means that v will be, as I mentioned earlier, tangent of x, because derivative of tangent of x is second square x. Okay, now this integral is equal to what? Let's remember integration by parts. We need to obtain a form of uv minus what? Minus v du. So in terms of what we obtained, it is, let's see, it's second to the n minus 2 of x times tangent of x, and let's not forget about our boundaries since we have a definite integral, minus integral of from 0 to pi over 4. Now v is tangent of x and du is, let's multiply this expression. We see that it's second to the n minus 2, right? Second to the n minus 3. We multiply this by second of x. We obtain second to the n minus 2. So we have second to the n minus 3, n minus 2 of x. And being attentive, we see that we also have tangent here. So let's just write it directly, that we have tangent square of x second to the n minus 2 of x dx, not forgetting about n minus 2. We also have n minus 2 here, and I'll move everything towards the left a little so that we have enough space for n minus 2. Since n minus 2 is a constant, we can move it out of the integral, so I'll write it here, n minus 2. I hope everything is clear up to this point. If you have any questions, please feel free to mention this exact moment and write this in the comment section below. I'll try to answer to all of your questions. Right, now we have second to the n minus 2 of pi over 4 times tangent of pi over 4. We are just opening up these, minus second to the n minus 2 of 0 times tangent of 0, and minus n minus 2 times, well, I won't rewrite this integral, I'll just write 3 dots here. You know that I mean this here. Okay, now we'll need to remember some values of secant and tangent on pi over 4 and 0. I don't remember in my mind, but we can quickly derive them, right? First, we have secant to the n minus 2 of pi over 4. Well, secant of x is 1 over cosine of x, so we need to find cosine 1 over cosine of pi over 4 to the power of n minus 2. Cosine of pi over 4 is square root of 2 over 2 to the power of n minus 2. And, well, because it's in the denominator, we can write this as 1 over square root of 2. These are the same. If you multiply this gentleman by square root of 2 and over square root of 2, we will obtain, well, okay, let me show this one time. It will be square root of 2 over 2. Okay, so namely we have then square root of 2 to the power of n minus 2 as the value of secant to the n minus 2 of pi over 4. Okay, then tangent of pi over 4, it's sine over cosine of pi over 4. Again, cosine of pi over 4 is 1 over square root of 2, and it turns out to be the sine of pi over 4 as well. So sine and cosine are have the same value in pi over 4. We know this from the circle as well here, because it's pi over 4, we have the same value. So tangent of pi over 4 is 1. They both have the value of 1 over square root of 2, so it's 1. Okay, we have finished with the first part of our expression. Remember, we had here square root of 2 to the power of n minus, it was 2, yes, n minus 2, multiplied by 1, I don't write this, minus secant of to the n minus 2 of 0. Again, 1 over cosine of 0 is 1, because cosine of 0 is 1, and tangent of 0, you might guess that it's 0, because it's sine of 0 divided by cosine of 0, and if cosine of 0 is 1, then sine of 0 is 0, right? So it's 0. Then it means that we don't even need this part, because tangent of 0 will be 0 and it's 1. So we have 0 here. Okay. Now we can move on to our integral, right? We have n minus 2 times integral from 0 to pi over 4. I'll rewrite this expression. It's tangent square x second to the n minus 2 of x dx. What can we do here? We can express tangent square x as in terms of secant x. Let me rewrite square root of 2 minus n minus 2 times integral from 0 to pi over 4. Well, if 1 plus tangent square x is secant square x, so tangent square x is secant square x minus 1, and we multiply this by secant to the n minus 2 to the power of n minus 2 of x dx. I used the following identity here. I'll make this as a remark. 1 plus tangent square x is equal to secant square x. Well, some of you may remember it, but if you forget all of these identities, as I do, you might just remember the structure of tangent of x. You know that there is, let's close it. You know that tangent of x is sine square of x over cosine square of x. You know that to obtain secant you need to add or subtract 1. Well, if you add 1, it's good, because in the numerator you'll have sine square plus cosine square, and this is 1. And we need to obtain something like 1 over cosine of square of something to have something secant-ish. So if we divide it by cosine of x, square of x, we have our identity. So if you remember this identity in your head, good for you. If you don't, then you have the clue. Oh, that sounded nice. I'll keep that part, I think. Okay, we move on to our problem. Now we have here, we continue, we have square root of 2 to the power of n minus 2 minus n minus 2 times, I'll multiply this here as a remark. Well, we have, well, I'm doing this right now, secant to the n of x minus secant to the n minus 2 of x, and this thing is inside of an integral, right? We have integral from 0 to pi over 4 dx. What can we do with this expression is we can separate this and write this as the difference of two integrals. We have integral of from 0 to pi over 4 secant to the n of x dx minus integral from 0 to pi over 4 integral of secant to the n minus 2 of x dx, right? Nothing special that I did. It's just, let's make some space here. It's just I rewrote this integral. Like first I wrote, well, tangent square of x as secant square of x minus 1. Then I computed this product together, obtained some expression, some difference of secant, and then to the logical end I just separated this integral with the difference in it to the difference of two integrals with this integrand. Okay, now if you are attentive enough, you can notice that this structure is something similar, right? It's actually I sub n that we introduced right here. Okay, so it means, and because these all expressions like earlier on, it's equal to I of n. We can derive some formula of I sub n. Let's write this in a more neat form so that our eyes can relax a little. It's n minus 2 times, well, what we have is it's in minus, it is itself indeed is I sub n minus 2, right? I sub n minus 2. Yeah, that's it. Now simplifying this a little further, we obtain, well, first the square root of 2 to the power of n minus 2 minus n minus 2 times I of n plus n minus 2 times I sub n minus 2. Now, because this whole expression earlier on, like here, is I sub n, we just write this here, it's equal to I sub n. Well, now we can write that, okay, I sub n minus plus n minus 2 of I sub n is equal to square root of 2 to the power of n minus 2 time plus n minus 2 times I sub n minus 2. From this we can just write 1 plus n minus 2 is equal to this, which implies that I sub n is equal to 2 to the power of n minus 2 plus n minus 2 times I sub n minus 2 over n minus 1, right? And yes, this is it. Now let's, for our future computations, let me just write this in a more neat way, right? Plus n minus 2 over n minus 1 of I sub n minus 2. We see some recurrence relation here. We obtained this formula for I sub n. Great. We are almost done with our problem, and now we can compute, with this identity you can compute integral from 0 to pi over 4 of any degree of second of x, like even second to the 74 of x dx, right? And deal with some longer expressions. What we need here is we need I sub 5. So let's compute this. I sub 5 is equal to, looking here, square root of 2 to the power of 3 over 4 minus 3 over 4 I3, right? Good. Now we can proceed and write that it's equal to, well, square root of 2 to the power of 3, it's 2 square root of 2, right? Because we have square root of 8 down there, and over 4 minus 3 over 4. With the same identity we can compute I sub 3, which will be square root of 2 to the power of 1, well, it's just square root of 2, over 2 plus, yeah, sorry, here we have plus, not minus, it's plus, and here as well. Okay, now we have square root of 2 over 2 plus 1 over 2 I1. Good. In the end we have, let's just compute this directly here. It's what it is. It's, if you have 8 here, it's 4 square root of 2 plus 3 square root of 2 over 8 right? I just multiply this by 2, and plus 3 over 8 I1. Now let's compute I1. From our definition, I1 is integral from 0 to pi over 4 secant of x dx. Is it? Yes, it is. Yeah. Well, integral of secant x is also a table value that you should remember. It has an interesting derivation, and I think I'll probably make a video on an integral of secant x. But for now, it's ln of secant x plus tangent x. And because it's an definite integral, we have boundaries from 0 to pi over 4. Okay, let's compute this here. It's ln, well, secant of pi over 4 is, what was it? It was 1 square root of 2, right? It was square root of 2, and plus tangent of pi over 4 was 1, minus ln of secant of 0 was what? It was 1, plus tangent of 0 was 0, and ln of 1, it's by definition 0, right? E to the power of 0 is 1. Okay, then it means that for I sub 1 we have ln of square root of 2 plus 1. Great. Then we have our final answer, which is that, like here, I5, which is also known as integral from 0 to pi over 4 secant to the 5 of x dx, is equal to, well, it's 7 square root of 2 over 8, 7 square root of 2 over 8, minus plus 3 over 8 ln square root of 2 plus 1. This is our final answer, and I'll just scroll one more time so that you can have a feeling of a process what we did here. If you have any questions, please feel free to write them in the comment section below. I'll try to answer to all of them, and see you on the next videos. Bye.